So in today's lecture, I'm going to talk about transformation matrices and why they're important to learn. So I use transformation matrices in the RoboSub vehicle. I use them to map out where each object was with relation to one another. And even if you haven't been over to a certain object and you don't know its transformation matrice, you'd be able to derive it from knowing where the other obstacles are with relation to one another. So I use transformation matrices a lot, and I wanted to kind of explain it to you guys so that you can get a better understanding of it when you look at the code or when you want to do some mathematical experiments determining where certain things are in the water, and this will really help you out. So the first thing I want to go over is Rodrigues formula, and what Rodrigues formula is it's a way to basically rotate a vector about another vector to get an end result. So for example, in this case, you have vector A and you're rotating it about vector K to get vector B. Vector B in this case is the result of rotating A about K. K must be a unit vector. That is very important. This won't work unless K is the unit vector. So K is the axis of rotation, and a lot of the times we don't like working with cross products, and it's the way how the math works out just tends to be a lot easier when you don't have to worry about cross products. So we do something called taking the skew of a value, and what that allows us to do is essentially multiply values, and that would be the same as taking the cross product of them. So you can see in this example, after replacing K cross A by K tilde A, you can get essentially the same exact thing. So the goal is to be able to just have this matrix, this right now we can consider like a magic number, a rotation matrix that you can multiply with any other vector, and you'd be able to get the resultant vector. So this is what the rotation matrix formula is. So you have your identity matrix, which is a 3x3 matrix that has ones all in the diagonal. You have your sine phi times k tilde, or your k skew, and what phi is how many degrees you'd like to rotate about the unit vector, in this case k. And then you have plus 1 minus the cosine of that angle, all multiplied by k skew squared. So to show you guys a little bit more about what the skew operator is actually doing to mimic a product or a cross product, is you're essentially taking the unit vector of k that you're rotating. It's the axis of rotation that you're rotating another vector by. You're expanding that into a 3x3 matrix, and this is what it will be. So you have 0, the third unit of k, so z, so negative z of the unit vector k, then z, then y, negative x, x, and then 0 all in the diagonals. And again, the purpose of doing something like this is so that you can just multiply A with the rotation matrix instead of having to work with the product, which this would not even be possible if you had to worry about the cross product. So being able to put it in the type of form like a skew allows you to just multiply the R and A together nicely. So here's an example. So you have the vectors A and B, and you want to rotate A about B by 180 degrees. So in this case, B is 0 in the x, 1 in the y, and 1 in the z. This is not a unit vector. Because it is not a unit vector, you need to be you need to convert it to a unit vector. So how you do that is the little hat on top of B shows that it's a unit vector. You have to take the vector and you need to divide it by the magnitude of the vector. So in this case, the magnitude of the vector is just all of its components squared, and you take the square root. So you get the square root of 2. So if you have the vector and you divide it by the magnitude of that same vector, you get 0, 1 over the square root of 2, and 1 over the square root of 2 for y and z. So now that we have our unit vector, we can proceed on to this line down here, the actual Rodrigues formula. So another way of describing rotation is by calling it a arot operator, where you have an operator of the unit vector and of the angle that you want to rotate it by, or rotate another vector by. So as you go on, you can see that here's the identity matrix, all ones in the zeros, or sorry, all ones in the diagonal. You're adding that to sine of the angle that that you want to rotate of A about B, and then this is the skew of that unit vector, and you're adding that to 1 minus cosine of that angle times that the skew squared. So when you do this math, it's just normal linear algebra. When you work this out, you end up getting this matrice right here. -1, 0, 0, 0, 0, 1, 0, 1, 0. So now, because you have that, you can just have the rotation matrice times by vector A, and you can get the result of vector C. This is the resultant of rotating A about K to get vector C. Or in this case, rotating A about the unit vector of B to get C. And here you can see this is what the rotation matrice was, and this is what happens when you've rotated it by 180 degrees. So the resultant of rotating it about B 180 degrees is 0 in the X, 0 in the Y, and 5 in the Z. So just like you can take the rotation matrice of the operators K and Phi, you can go back and you can just have a rotation matrices and you can get K and Phi. So these are good for situations where you know your rotation matrice, but you want to know what your axis of rotation and the angle that it's rotating about is. So when you do the arot operator, this is what the solution will be, where it will, if you want to calculate your phi, or the angle that you're rotating about, you take the arc cosine of both sides, and you'll have this value. So it's 1/2, so it's arc cosine of 1/2 times the trace of the rotation matrice minus 1. So the trace of the rotation matrice, it sounds fancy, but all it is just adding up the diagonal components of the matrice. So below you can see right here that this is a matrice, and all I'm doing is adding up the units diagonally. So if you follow this order, you'll get the angle that the rotation matrice has. And in addition to that, you also need to derive the unit vectors of K1, K2, and K3. And this is how you do it. But it's as simple as plugging in the equation at this point, but unfortunately there are degenerative cases where what happens if phi is equal to, let's say, 0. If phi is equal to 0, then sine of 0 is 0, and you have 0 in the denominator, and that doesn't work out. Same case for when you have 180 degrees for phi. So in case of the degenerative cases, what you need to do is you can use these equations instead, and what this will allow you to do is not have that issue where you're dividing by 0. And any one of these solutions will apply, but you just need to pick one that won't have a -1 in the square root. Because let's say if the rotation matrix, or let's say the unit R11 of the rotation matrix is, let's say, -3. So that means you have -2. So there's a negative number in the square root, and that doesn't work either. So you need to pick any one of these cases, just one, that won't have an imaginative number. So here are some of the rotation properties that I just wanted to throw up. I'm not going to go through all of them, but they're really nice to just see how this really is just a normal operator, and how the different options that you have for manipulating the rotation matrix. So when you're multiplying the rotation matrix by other things, or when you're doing some things with it, you might be able to simplify it a little bit more. So I'll leave this here so that you guys can just refer back to it if you ever want to see it. So I want to go over basis vectors. So what basis vectors are, in the pure simplest form, is it's just a unit vector representing the x-axis, representing the y-axis, and representing the z-axis. So it is a vector in the x direction, a vector in the y direction, and a vector in the z direction. That's where you get E1, E2, and E3 from. So if I had something like this 3x1 matrix where I have A1, 0, 0, 0, A2, 0, and 0, 0, A3, an equivalent statement of that is multiplying A1 by E1 plus A2 times E2 plus A3 times E3. This is important to know for when you want to use the rotation matrices for rotating about the x, y, or z. So this is what these matrices are, is essentially, without having to go all the way through the Rodrigues formula, you can use these matrices to just have the rotation matrix. And this is very convenient because oftentimes you are just rotating about the x, y, and z. And most times you can just get away with rotating it about x, and then rotating it about y, and then rotating it about z to get your desired rotation matrix, instead of just doing it all at once and you having to use the Rodrigues formula. So if you can commit these to memory, I promise you it's going to serve you a lot in the future. So we talked a little bit about rotation matrices. There's also something called translation matrices. So like before, what I said was we didn't like cross products because that made it difficult for the math to work out properly. The same thing goes for adding vectors. So when we add vectors like A and D, you put the tail end of D at the head of A, and then you'll get vector B, which is the resultant of A plus D. There's another way to do this where you can get it in the form of multiplying one matrix with another, and that's what we want to do because the math, again, will work out a lot simpler for us. So first, what you have to do is, and don't let this confuse you, this hat right here, this does not necessarily mean a unit vector. In this case, this means it's an augmented vector. So you have to realize on a case-to-case scenario what exactly you're dealing with when you have the hat on top of the vector. In this case, they're augmented vectors, and in order to get the desired trait of adding two vectors together, you can refer back to this top right diagram up here where the translation matrix is going to be a 4x4 matrix. That's just how the math works out. So this, I've expanded it out down here where you have an identity matrix in the top left. You have 3 zeros in the bottom left. You have a 1 in the right. And in the top right, you have the x, y, and z, how much it's translated by. And when you multiply a vector by this 4x4 matrix, you will get the A plus D that we're looking for. So back to augmented vectors, how you make an augmented vector is all you do is just add a fourth dimension to the vector by 1, because we're dealing with a 4x4 matrix. We can't do math with a 3x1 matrix. We have to expand that out to another dimension so that the math will work out correctly when you multiply a 4 by 4 with a 4 by 1. So after turning this into a translation matrix, you're able to do something as simple as this, where you take the translation matrix and you multiply that with a vector to get vector b. So if you refer to the diagram up here, that's essentially what this is doing, where you have this vector a and you're timesing it by a translation matrix and you're getting vector b. So let's recap. We've talked about pure translation and we've talked about pure rotation. So like I said before, the whole reason why we did augmented vectors is so that we can get it into the form where we can multiply with the translation matrix. When you want to multiply a rotation matrix with a translation matrix, the same thing applies where you have to do an augmented matrix. And in order to do an augmented matrix, it's denoted by capital ROT for the capital R instead of just smaller ROT. But this essentially adds another dimension to the matrix that allows you to multiply the values, which we will do later on. But if you wanted to combine the translation and rotation matrices, so you just multiply a vector by something called a transformation matrix, which is the combination of both rotation and translation, it's as simple as putting the rotation in the top left corner that used to be the identity matrix for the translation matrix. So you have the rotation matrix in the top left. You still have zeros in the bottom. You have the 1 on the bottom right, and you have the x, y, and z for the translation in the top right. And here it is in expanded form. The deltas here are the distances that you'd want to travel along in the x-axis. In this case being a unit vector, so k1, so if it's 1, 0, 0, k1 is 1, k2 is 0, k3 is 0, then you just say to this delta how many units you want to go into the x-axis. So to sum it all up, let's do an example of this. So we have vector A, and the question is asking us to determine what's the combination of translation and rotation matrices to get vector A to vector B. In other words, what's the transformation matrix to get A to multiply by this transformation matrix to get B? So one thing that I'd like to stress is when you are translating and rotating vectors, you always go right to left. Always. So in this case, when you have the vector A, which is in this case 6 units in the x direction and 1 unit in the y direction, so here's the 3 by 1 matrix, or 3 by 1 vector, you take that value, this is right to left, you translate it in the y direction first by a distance of delta. In this case, delta is 2. So you translate it along the y-axis, denoted by the E2, because before when we looked over basis vectors, you saw that E2 represents the y-axis. So translate it along the y direction by delta, and then after you've translated it, you want to rotate it about the z-axis by 30 degrees. The reason why we do the z-axis is because if you do the right hand rule and you stick your thumb where the z-axis is, if you want to rotate along 30 degrees, you go in the direction with your hand that's normal to you. If you wanted to go negative 30 degrees, you'd go in the opposite direction. So you have your A, you've translated it, and then you rotated it. So if you multiplied the translation and rotation matrix, you'd get a transformation matrix, shown right here. So if you look at the translation matrix first, you can see that there's the identity matrix, and you have 0, 2, 0, showing that you're just moving in the y-axis by 2, and that's multiplying by a rotation matrix, which is zeros for all the positions. and then your rotation matrix is right here, following these rules about rotating about the x, y, and z axis. When you multiply these, you'll get the transformation matrix, where you have a combination of the translation side, which is -1 in the x, the square root of 3 in the y, and 0 in the z, and you'll have the rotation matrix here. So now at this point, all you need to do is multiply the vector that you want to transform by this transformation matrix. It's as simple as that. So you know that this was a 6, 1, 0, but you need to get this into a form that's an augmented vector. So now you have 6, 1, 0, 1, and you're multiplying it by the transformation matrix to get your desired end vector that's transformed. You'll have a 1 at the end, so all you need to do is tack that 1 off, and then there you have the unit, or there you have not a unit vector, but you have the vector of the end result of transforming that by the rotation, or by the translation and rotation. So here's an example that you should do by yourself. So you should pause the video and see if you can figure out what the transformation matrix of this problem is. So this is what the answer is. So you would rotate it along the z-axis by phi, and then you would translate it along the y-axis by 3, because there's 3 units here that it needs to go up in the y-axis by. And in doing so, when you take the rotation matrix and multiply it by the translation matrix, this becomes the transformation matrix of the problem. And another thing to note that's important here, remember that I talked about the arot, or arc rotation. This would be great for cases where you have where you're multiplying a bunch of rotation and translation matrices together, and you'll get some sort of rotation matrix in the end result, in the transformation matrix. You can pick off the rotation matrix, this 3 by 3 right here, and do the arot and get the overall unit vector and the angle that the vector would be traveling around. And this is very desirable when you just want the overall unit vector and overall angle that it's spinning.